language in OCaml by Dimitri?
Yeah.
Yeah. Please test when you are ready.
Hello? Hello, I am Dmitry, and we will talk today about relational programming. The basic idea behind relational programming is to represent functions, programs not as functions, but as relations. And there are quite a few relational programming languages. For example, you can do relational specifications in Prolog, in Mercury, but in this talk we'll stick with Miniconran. There is an introductory course about Miniconran, the code Relational Schemer, by Oleg Kiselev, William Bird, and Dan Friedman. And Miniconran is a domain-specific language initially implemented for Scheme and Racket. And it has rather simple minimal implementation. And also, there is a whole family of Miniconrans which extension introduce some new cool feature into basic language. And Miniconran has been embedded into many host languages, both typeful and typeless. So we created a new implementation of Miniconran called OCaml, and I will show you how programs look like in OCaml, OCaml, and original Miniconran. So we have very simple list concatenation function, which returns the second argument when the first argument is empty list, and otherwise it destructs first argument, does a recursive call, and prepares head to the result. When we rewrite this in relational specification, we first of all promote the result into relation arguments. Usually relations are named by appending the superscript O to the original name. Our pattern matching has two cases, so we'll have two subformulas connected with a disjunction. The first subformula is rather simple. When first argument is an empty list, XYS and YS are the same. And the second part of the formula is rather long because we need to introduce temporary variables for destructing our arguments and for calling relation recursively. So it looks like that. We have used there a little bit of macro to hide different instantiations of fresh variables, and we did it in one line. And these little formulas, they are implicitly connected with conjunction during the macro expansion. And this code should not be rather it is not longer than original Miniconran implementation. There are a few differences, but they are syntactic one. So, when you create a new implementation of Miniconran, you usually look into minimalistic implementation called microconran, and you deal with notions related to relational programming like logical variables, symbols, terms, substitutions, and unification, which is a primitive which takes a substitution and two terms and tries to make these terms similar. And it can fail. Also, there is a technical notion of state which holds current substitution, some information how to introduce new fresh variables, and maybe some constraints on variables if we implemented constraints. The goal is a function from state into stream of states, and it converts current state into lazy list of answers. And this lazy list is a monad, and when you need to implement another search algorithm, you rewrite these two functions, monadic bind and monadic plus, which correspond to conjunction and disjunction respectively. Also, after evaluation, you need to look into the state and get the real value of introduced logical variables. It is called refinement. And the main things to implement for minicanon, the main interesting things are unification and refinement. Let's look how we should not do this. The naive approach is to create the universal type, which is, let's say, called term, and we force programmer to write his own conversions from his type into term and back. But it will be difficult to do type checking because we will not know from which types these two terms has been created. For example, we create a term from integer and another term from string, and we can't throw a type error because we unify two different type terms. So it is not really a good solution. The nano solution is for every user type to generate specific unification code, but is very boilerplate, and the user still need to think where in his types logical variables will be stored, and it's better to avoid this. The third approach is to implement really polymorphic unification, which deals with any pairs of terms of any type, but these terms should be the same type. And we tried to do this, but there are some problems because it should be implemented in a typed manner. But it will be a very lightweight and good solution if we can prove that type safety will be preserved. So we implemented unification for logical variables and refine for them. There are a lot of tricks, and you can make a lot of mistakes when you use unsafe features of OCaml. And we basically have adopted the same approach like OCaml polymorphic comparison and polymorphic equality are implemented. You can, well, you don't have type term anymore, so it is difficult to decide which type of your substitution will have, because it will be a heterogeneous map from logical variables to any values. So we decided to erase these types and implement refinement well. And we need to prove that unification and refinement are done correctly, and the states which are used during refinement can escape the scope. In this case, we'll lose a link between logical variables and states where they were introduced. So we have in a paper an algorithm which describes how to do unification, and we implemented this algorithm. And it should work and should be correct when variables in substitution always substituted to the terms of the same type. I mean, when we substitute variable into term of type t, it can be later substituted into another term, but this another term should also have this type t. And the second, during execution, logical variables should not change its type. They save the type assigned by a compiler. And when we unify some values, we should always unify values of the same type. So to make refinement type safe, we need to deal with the states, the runaway states, which can bring some errors and runtime crashes, and capture the states. And to do this, we implemented a top-level primitive to run relations we have been declared. It's called run, and it has three arguments. The first one is numeral, which represents how many logical variables will be used by our relation. When we partially apply this run function to a numeral, the result will be a truly polyvariatic function on two arguments. The first argument will have as many logical variables as specified, and the handler will take as many lazy lists with refinement answers for every introduced logical variable. So this framework guarantees that variables will be refinement in the right states. A few slides ago I have said that we should provide some generic way to create logical variables, and a user should not think how he should do this. He should not write code manually. And the basic idea behind this is to use functors to represent types. Let's say we have this tree, and user will write a functor for this tree called treeF. And when he specifies these type arguments in the right way, for example, very naive way, he will get original type tree, and these two tree types will be identical because compiler is smart enough. But when he will substitute type parameters by logical equivalents, for example, int logic and logical tree, he will get truly logical type which represents logical trees. And if he will use some generic framework to derive fmap, it will be possible to write conversions from this tree logical type to original tree and back. There we use fmap for specific tree and use arrow operators which convert to and back from logical domain. And arrows with quantifier are just shallow injection and projection. It just wraps values on top level in the root. An example. So, relational programming allows us to write code in rather declarative manner. There we implemented sorto, the function, the relation which just sorting. So, when you should sort a list, you should find the smallest element and put it in the beginning, and then sort the tail of the last other elements of the list. So it is described like this. It's our sorter function. In the bottom of the screen, we will generate permutations of a given list. We will use, described in the previous slide, functions to convert this list to logical list. And after that, we will sort this logical list and get the sorted list. And to get all permutations of sorted list, we should call function relation sorter backwards. So we specify first argument as logical variable is here, q, and r is result of sorting. And after running backwards, we take results and print them. So we receive all permutations all using predefined sorting function. As a conclusion, I have said we created yet another implementation of mini-conran. It is based on micro-conran, and some disequality constraints were implemented. And on long queries, it works faster than scheme implementation. Any questions?
One thing that I like in ML and that don't like in scheme is algebraic data types. You can use them and they don't. But in your style, it feels like, so you can faithfully represent the scheme examples, but I would like to be able to use pattern matching to write the same logical function. So is there a way you could have some syntactic sugar on pattern matching that we use it?
Well, in scheme there is a macro called matcho, I think, yeah. And it shortens pattern matching related code.
But could you have such a thing in your implementation?
Well, I think we should write some ppx macro, it will be okay.
So the automatic conversion between a type and its logical counterpart is important when you want to write functions, for example, list, using logic programming. But in practice, I rarely do that. And when I have a need for deep unification and backtracking and so on, it's some interesting problems that don't handle list, but some more difficult data types, like, I don't know, group terms or something like that. So, do you think that for real-world use of your library, I will actually need a lot of conversion functions? Maybe I can just define my own logical types from the start and just use that.
Well, define your logical types in the beginning and use them. We have some examples with a little bit more longer algebraical data types with free constructors to implement lambda calculus and relation temperatures of this lambda calculus. So it kind of doesn't see any issue. I don't see any issue.
Can you give any hint as to the differences in benchmarks behavior, both the reasons that you're getting performance improvements and any hint as to what tests your implementation is providing different behavior?
Not really, maybe offline.
Which scheme implementation did you use to test microcanon?
We use it microcanon, which is not as fast as our implementation on long queries, but there is also faster minicanon project, which does, I think, substitution a little bit different way, but we didn't adopt their approach. So at the moment, faster minicanon in scheme is faster than our minicanon.
Okay, but what scheme implementation did you use? What scheme implementation is microcanon running on top of?
Well, we usually used Racket, I think, and some scheme, I'm not sure.
Okay. Thank you very much.